Now that we have a good foundation in understanding stars, we can start thinking about the largest grouping of stars, which is galaxies. And we'll start with our own home galaxy, the Milky Way, and think about how big it is and what its shape and structure are like. Okay, now first, you should go out and try to find the Milky Way. If you haven't already, this is something you should definitely put on your to-do list. It's best if you can find a moonless night, so the sky is as dark as possible. Try to get away from any city lights and house lights. Pick a sort of dark part of the sky to just stare at, and that will let your eyes adjust and start bringing out where all the little points of light are coming from. And if you're in a dark place and your eyes have adjusted, you'll probably start to see this broad swath of brighter regions of light across the sky, and you'll have found the Milky Way. In an image like this is a long time exposure, so you won't see it looking as it appears here, but you will get a really impressive view of our galaxy and what it looks like from here, where we are located in the galaxy. A couple numbers to keep in mind about the galaxy, the Milky Way. There are about 250 billion stars. So we are around one of 250 billion stars in the Milky Way. And it's about 100,000 light years across. So from one end of the galaxy to the other, it takes light 100,000 years to get there. Now, we haven't always known we lived inside a galaxy, and we haven't always known what that galaxy looked like. The earliest map of the galaxy we have was created by William and Caroline Herschel. This is in 1785. And their observations of where stars were located based on looking at the night sky through telescopes and naked eye was that it sort of stretched out in a disk. Now, when we compare it to the detailed observations we have now, it's not very good, but they did get the basic overall shape of a disk, that it's not kind of spread out the same in every direction. It's aligned in a disk. Now, part of the reason it's hard to observe the Milky Way is there's a lot of dust in the galaxy, so many of the stars are not visible, or their visibility is dimmed by the dust that's in the way. And that certainly affected how well they were able to observe it back then. But they estimated that the galaxy was sort of shaped like this. Now, why would it have this weird missing region? Well, there's probably a lot of dust in that direction, and so they couldn't see stars there. So they just imagined that there was this weird lobe kind of emanating off of the disk like this. But the sun they had at relatively near to the center of the galaxy, because they were able to basically see about the same number of stars in every direction, and so you imagine that you must be at the center of whatever this is. Now, obviously, today we have much better technology, much better observations, and we can look at the galaxy in different types of light. Now, with a nice telescope, in visible light, one of the best images you can get is the one on top here, right? And you'll notice a lot of the galaxy is being blocked by these dark regions. That's the dust that's in the galaxy. Now, the dust will preferentially block the shorter wavelengths. What that means is that it's easier for long wavelengths to get through the dust than for short wavelengths. The short wavelengths get absorbed and blocked more easily. So, in visible light, the visible light has relatively short wavelengths, and so they get blocked. We don't see the light from the stars that's on the other side of this dust. Now, if you want to get rid of the dust, what you can do is look in a different part of the electromagnetic spectrum, go to a longer wavelength. So we go from visible into infrared, and immediately the shape of the galaxy becomes a lot more clear. Now here you can tell that it's a disk, but here you can tell it's a disk with a big bright bulge in the center. And you can see that the center of the galaxy is here. Now in this picture, it's mostly blocked. So infrared gives us a much better view of the galaxy. If you remember back to when we were talking about telescopes, the Hubble is sort of centered around the visible spectrum, giving us a good look at what the galaxy looks like in visible light. The James Webb Space Telescope, when it becomes operational, it will give us a much better look at infrared light. And part of the reason we've designed it that way is so that we can penetrate deeper into the galaxy and outside of the galaxy to look at things in wavelengths that will get through the dust that exists out in space. All right, now what does the galaxy look like from other perspectives? Obviously, we haven't been outside of the solar system, so I can't show you a picture of the Milky Way from any different angle. I can only show you what it looks like from the vantage point of the sun. I can only show you a real picture of the Milky Way from the vantage point of the sun because we've never really left the solar system. So, what does the galaxy look like from those other vantage points? We know that there are three basic types of galaxies from looking around at galaxies across the universe. There are these spiral shapes, then there are elliptical shapes, which are sort of shaped like ellipses. You can't see any spiral arms. And then everything else we throw in a catch-all category called irregulars. So irregulars could be any shape that's not a spiral or elliptical. So then we can ask, what type is the Milky Way? Well, the Milky Way, based on observing it just from the sun, we've been able to determine is a spiral galaxy. It has spiral arms, and even more specifically than that, it's a barred spiral. And that's a specific type of spiral where it's not totally symmetric. Now see the picture on the top here, this is an unbarred spiral. It's just what maybe you'd call it a regular spiral. And it's symmetric in the sense that you could kind of draw a line across it in any angle, and it would be sort of the same on the left and on the right. So if I drew a line this way, there's about the same amount of galaxy over here as over here. And you could kind of draw a circle around the whole galaxy. A barred spiral has a little bit of an asymmetry to it, and this is an example of what a barred spiral looks like. And it's called a barred spiral because it sort of looks like there's a bar running through the middle, like this, that breaks the symmetry a little bit. So instead of looking the same if you draw a diagonal this way or this way, it has a specific axis of symmetry, like across the bar. Well, we've determined that the Milky Way is a barred spiral galaxy, so we probably look a little more like this than this. Now, for more detailed observations of what it looks like and what the anatomy of the galaxy is, we can look at this image here. So there's a central bar, because it's a barred spiral, and it has several spiral arms, and each of those arms have names. You don't need to know the names of the spiral arms of the galaxy. That's not something I'm going to ask you about, with maybe one exception, and that's just to know where we are located in the galaxy. We are located in the Orion Spur. So this little region here is called the Orion Spur. I'll give you a closer up look at this in a minute. That's where the sun is. So this is kind of a top-down view on top of the galaxy. Notice we're not near the center, so the Herschels weren't quite right in their placement of the sun in their original picture of the Milky Way, but they were just limited because they could only kind of see the stars in this vicinity. They couldn't penetrate the full depths of the galaxy to see that, wow, there's actually a lot more stars over here on this side of the sun than there are over here. Their window of view was just kind of this part of the galaxy. There's plenty of stars to look at right here. So when we talked about when we did the lab on the nearest and the brightest stars, most of the stars are kind of that are in that category. Certainly the nearest, but also the brightest are generally in the range here. Right? We're not really getting a lot of stars from the center of the galaxy, as you could tell from how much dust blocks the center. If you flip the galaxy and look at it sideways, now we're over here. So the sun is in the middle of the disk, about 26,000 light years from this center, which is called the nuclear bulge. So the galaxy bulges out at the center. It's wider there than in the disk part. That's called the nuclear bulge. And then surrounding the galaxy are these globular clusters, which we talked about previously. So they kind of orbit around the galaxy. They're outside of the main disk. So kind of sort of like mini galaxies themselves orbiting the larger Milky Way galaxy. All right, now here we have another map, and I bring this up because it shows us a closer up look at where we are located in the disk of the galaxy. So here's the sun in the Orion Spur. So it's called the Orion Spur because that's where the Orion Nebula is found, which is in the constellation Orion. That's another thing to put on your to-do list if you come across someone with a telescope or you have one for yourself or some nice binoculars. Try to find the Orion Nebula. It's just below Orion's belt on the left. And so we're not too far in relative terms from the Orion Nebula. And if you look at a closer up view of where that Orion Spur is, it's not really a full big spiral arm in the galaxy. It's sort of like a little spur coming off of this larger Perseus arm, right? So the Perseus arm comes through here, and then there are sort of these connecting spurs that go in between them. So it's not perfectly spiral arms everywhere. Now, the formation of galaxies is something that's still under study. We don't know this maybe as well as we'd like to. But this picture here will show you how you could imagine spiral arms starting to form. But it also leads to something that doesn't quite make sense. So let's kind of go through that. You start out with two big clouds, and they're close enough together and far enough away from everything else that they become gravitationally attracted to one another, right? The curved space from this big mass of gas and dust starts to connect with this curved space from this mass of gas and dust, and they begin swirling around one another in space. And as they swirl around one another, they start to form these spiral arms. But if you just keep fast forwarding, these spiral arms should wind tighter and tighter and tighter and tighter. And our computer models suggest that that can't last forever. The spiral arms will eventually sort of twist themselves into just a flat disk. But what allows the spiral arms to persist is that it doesn't happen quite as simply as this, and there's actually turbulence involved in the fluid flow, and that turbulence causes the spiraling to slow down so that the rotation reaches an equilibrium and those spiral arms don't twist on top of one another and get kind of bound up. And so this is something that astronomers are actively trying to understand a little bit better, is how you go from the initial stages of gas and dust clouds into a nice stable equilibrium galaxy. All right, so another look at what the galaxy looks like with things labeled. Just putting this up here in case this one helps you label the pieces a little bit easier, because there's less on here to be distracting. So we've got the sun in the disk, the bulge at the center. The disk is thin in the middle. That's where most of the star population is, but then there's sort of a thicker disk around that where there's another population of stars, and then there's the halo surrounding it. And the table here distinguishes what those different parts of the galaxy are like. There's the thin disk, the thick disk, and the halo. And you can see that there are differences in terms of what the stars are like in each region of the galaxy and how much material. For instance, the thin disk, 4 times 10 to the 10 suns. The halo, just 10 to the 10 suns. So there's about 4 times as much star mass in the thin disk as there is in this entire halo. And the thick disk is only a few percent of the thin disk. Okay, So another view of galaxy formation, galactic formation. We're starting up here in the upper left with a single cloud now. In that single cloud, gravity is going to pull everything in, but you have to imagine that that cloud will initially have some amount of rotation. It's very unlikely that that cloud would be perfectly still, and it's much more likely that as the dust cloud contracts, it will be rotating somewhat slightly. As it rotates and contracts, the contraction is going to actually cause the rotation to spin faster. This is sort of like an ice skater spinning with her arms stretched out and then pulling them in tight. The pulling them in tight makes her spin around faster. The same thing will happen here. The principle here is called conservation of angular momentum. And due to that, as the cloud contracts, it will start to spin faster. And another analogy here is with like a pizza dough. If you spin a pizza dough, it will flatten out into a disc. So you have a couple of effects here that are working together. Everything is being pulled in because of gravity. As it's pulling in because of gravity, it's spinning faster, and the spinning is making it flatten into a disc. And then as it's flattening into a disc, now the gravity is the direction of gravity is given by these arrows. Instead of it pointing all towards the center, this side of the disc is pulling on this side of the disc, and it's sort of causing it to even flatten out further and further. And eventually it reaches this equilibrium state where the whole galaxy is spinning. You have the generally roundish bulge in the center, and then the flat disc. Now, one more point on this before we move on. The halo, the clusters in the halo. We know that those are older stars. Why might they be older? Well, because they were clustered together early on here in stage 2. They could sort of get to the business of star formation before this massive cloud here. So these things went to work immediately here in stage 2, starting to create stars. Star formation didn't start here in the rest of the galaxy until later on, after these things contracted enough to create the pressure where stars could start to form. And that disk could sort of fragment into chunks of stars. And so generally speaking, disk stars are younger than the globular clusters surrounding the galaxy. Okay, now one more thing before we end this video. This is our nearest neighbor big galaxy. So we are part of a local group, what's called the Local Group of Galaxies. It includes the large and small Magellanic Clouds, which are visible from the southern hemisphere, and the Andromeda Galaxy, which is visible from the northern hemisphere. The Andromeda Galaxy is actually the biggest of the local group. So the Milky Way is not the biggest galaxy, even in our own neighborhood. This is a telescopic view of Andromeda. It is something you can find with a good telescope and a little bit of patience. So if you have that opportunity, I recommend trying to. It's kind of neat. You'll see like a clear gray. You won't see this color probably, but you would see a gray fuzzy spot that would be clearly distinct from what a star looks like or what a planet looks like. Now, just to point out the size difference, I mentioned about 250 billion stars was the estimate at the very beginning for the Milky Way. Andromeda, we estimate, has about 1 trillion stars in it. So it might be about 4 times the size of our own galaxy. Now, they're part of a local group because they're gravitationally around one another, and eventually our models predict that those two galaxies will collide. The Milky Way and the Andromeda will collide. And this here sequence of images is simulating what that collision might look like in our sky. Now, this is fast forwarding pretty far into the future. So if you look at I left the caption in this one. In about 3 billion years, they'll start to collide. So we're going to already start to have some problems with the sun by then. So if you're worried, are we going to be around to witness this? Are people going to be around? There's lots of variables in addition to this. But if we are in the same neighborhood of the galaxy in 3 billion years from now, we expect to have a view something like this. The two galaxies will merge. That will actually trigger a bunch of new star formation. The shapes of the galaxies will become completely distorted. So two spiral galaxies will eventually look like an irregular galaxy for a period of time, stages 2, 3, 4, as they pass through one another. Then, over time, as new star formation is triggered and the dust and gas sort of settles, you'll eventually form into an elliptical, sort of a blob, roundish shaped galaxy like this. And so this might also be a hint at why we have these three types of galaxies. That maybe when you start with an initial dust cloud or two, it evolves into a spiral. When spiral galaxies collide for a time, they will look irregular, and eventually they would settle into an elliptical shape, having had all of their spiral structure sort of taken away, and becomes a lot more homogeneous as a result. All right. So in the next video, we will look at a couple of interesting observational findings about the Milky Way, dark matter, and the supermassive black hole at the center of the galaxy.